Well, today's topic is changes of state, and in particular, we're going to take a look at how the kinetic theory of matter explains what happens when you changes of state. Changes of state are when we change from solid to liquid to gas and back. First of all, let's explore the kinetic theory of matter and what it asserts. It says, first of all, that all matter is made up of tiny particles. Atoms, molecules, ions, everything that exists is made up of these little tiny bits. The particles have an attraction to one another, and I like to model that attraction as a spring. If there was a spring actually connecting these two parts, as they moved apart, energy would be stored. As they move closer together, energy would be released. So that's our model that we're going to use for particles. Another thing is the particles are in constant random motion. As they're sitting there, they may not look to us macroscopically like anything's moving from what we can see in our eyes, but really all the particles are constantly moving around. Another basic to the kinetic theory of matter is that the higher the temperature, the faster the particles are moving. In other words, temperature is a measure of kinetic energy. If you look at this little example here, when the thermometer shows a low temp, the particles are not moving that fast. But if the temperature rises, as we see here, the temperature's gone up, well, then the particles are vibrating more rapidly. That's a basic idea behind the kinetic theory of matter. The temperature really is just a measure of how fast the particles are vibrating. Another basic idea that can be tied into this, and this has to do with changes of state, is since these particles are attracted to each other, as you pull them apart, they're going to store energy in those attractions. So the particles that we have down here, they're much farther apart. Well, those particles are going to have more energy stored in them than when the attractive particles are left close together. It's just like pulling apart two magnets. Conversely, then we could say as the particles are moved closer together, they're going to release energy. So if you have particles that are far apart in one phase, like the gas phase, as you put them closer together, well, that's going to release energy. And we see that happening macroscopically. So looking at changes of state, imagine a solid. What a solid really is a network of all these particles that are connected together by all these little attractions that I'm modeling here as springs. Watch what has to happen for these to get farther apart and become a solid, because that's really what's happening when solids are changing into liquids in general. Stretching all those little springs takes energy. So to move from the solid phase, where the particles are close together, to the liquid phase, where the particles are farther apart, takes energy. Energy has to go into that. And so melting is an endothermic process. Ice doesn't melt unless it's warm outside. Conversely, freezing, because it's the opposite process, has to be an exothermic process. In order for the particles to get closer together, like they would have to be for a solid, energy's got to be released to the surroundings. So going from the liquid state to the solid state, freezing, that's an exothermic process. Put your hand back behind a freezer sometime. It's warm back there because energy has to be extracted from the things that are in the freezer. Vaporization, the process of going from a liquid to a gas, is very endothermic because the particles are getting much farther apart than when they're just changing from solid to a liquid. Liquid particles start out close together. Gas particles are very far apart from each other. In fact, to scale, there would probably not be more than one particle on the whole screen if we were really modeling this to scale. So the reverse is a very exothermic process. When condensation happens, a gas, like say water vapor, becomes droplets of liquid on the outside of a cold glass of Kool-Aid or something like that. Well, that process has to happen in a cold environment, hence the cold glass. As the process of phase change takes place, the energy that's added isn't always going into making things hotter. Remember, temperature is a measure of kinetic energy. So what's going on here is, this is an example of what's called the heating curve for one substance, a common substance, water. If I start out at, let's say, 20 below zero, and I add energy, so on this axis I'm showing how much Q, how much energy I've added. On this axis I'm showing how much the temperature has changed. I see that the temperature is going to rise pretty steadily over this first phase. Add some heat, the temperature is going to go up. In other words, the particles are going to vibrate more rapidly. Once I get to the phase change temperature for water, that's 0 degrees C, then the energy no longer goes into increased kinetic energy. The energy now is stored in the positions of the particles. So as the liquid particles move farther apart from each other, I have an increase in Q, but I don't have any increase in temperature. The amount of energy that would take for water is called its molar heat of fusion. It's abbreviated delta H FUS for fusion. And for water, that happens to be 6.008 kilojoules for every mole of water that you melt. So this process is melting. Then, once the water is all melted, its temperature can then begin to increase. So for a phase here, as we go through liquid, as all the particles are liquid, increases in Q, increases in energy, go into increasing the kinetic energy, until we get to our next phase change temperature, which is 100 degrees C for water. At that point, the water begins to boil. And once again, the energy added goes into not increasing KE, temperature stays the same, but into going into PE. So the particles get farther apart. Their potential energy increases, but their kinetic energy does not. This is vaporization. That's this process right here. And the amount of energy it takes to get through that phase change for water, every substance has its own, but that's called delta H vap, and for water it's 40.79 kilojoules for every mole of water that you vaporize. Then once it's all vaporized, the steam, the water vapor, can then begin to increase in temperature as you add more Q. Let's take another look at this. This little animation here can give us a sort of a picture of what's happening with the particles. Imagine that this is a block of ice right here in the center of this glass. It's got fire underneath it. And we've taken like every trillionth of a particle or whatever and made it show up as a blue speck. So there are many, many, many more water molecules in a block of ice than this. These are just a few representative particles, and we're taking a look at the constant random motion that would be associated with their movement. So let's get this fire going and see what happens. Look at the temperature. Right now it's 20 below Celsius. Follow what happens. As the temperature rises, the particles start to jiggle faster and faster. That's what we'd expect. Once it reaches 0 degrees C, however, they're just jiggling the same rate that they always were, but now the stuff is starting to melt. But now once it's melted, the particles can then again begin to jiggle more rapidly. Well, that's the part of the phase diagram where we're going up in temperature with added heat. So as the heat continues to be added into these particles from the fire down here, that now goes into increasing kinetic energy. Once in a while you see a particle escape. Once you get to the boiling point, all that happens is particles escape. The kinetic energy, the rate of speed of these particles stays the same. They're still jiggling at the same rate, but now they're beginning to pull apart from each other, which increases their potential energy. So phase changes increase potential energy, not kinetic energy. Once the water's all boiled, well, then you can see that the temperature will begin to rise again. And the temperature of the steam can get higher and higher, and they can move faster. And so they're all going to vibrate to the point where they just get right out of the container. Well, we could do an example problem related to this by asking ourselves how much energy would be required to vaporize 56 grams of water. We know that this is based on per mole, so we could start out by taking our 56 grams of water and changing it into moles. The molar mass of water turns out to be 18.015 grams. 2 hydrogen masses times 1 oxygen mass. So that gets us into moles. And then we know that vaporizing takes 40.79 kilojoules of energy for every mole of water. So multiplying by that factor is going to give us how many kilojoules does it take? And the answer is 127 approximately kilojoules. Here's another problem. It asks how much energy is released when 24.3 grams of water is frozen. Well, you can do this a very similar way. Starting out 24.3 grams, we know we have to first of all change this into moles. So 18.015 grams per mole. That gives us moles. And then for freezing water, 6.008 kilojoules are going to be released for every mole. That's the molar heat of fusion. The amount of energy it takes to melt water is exactly the same as the amount you'd have to release to freeze water. The answer here is 8.104, and the unit is kilojoules.